Hi guys, today we're getting started on our very last unit for first semester, so Unit 5 on kinetics. And today we are going to start with these first two sections, reaction rates and then something called rate laws. So let's go ahead and get into it. All right, let's just talk about some general reaction information first of all. So some things that you need to know about reactions: that in order for reactions to take place, chemical reactions, molecules have to collide. And when they collide, the more often they collide, the faster the reaction is going to happen. They also need to have enough energy, which we've talked about, I think, really briefly in a previous unit, talking about activation energy. When it has that correct amount of energy, those molecules are able to rearrange and react and form new products. So there are some things you guys need to know about that affect the rate of reaction. Rate is how fast reactions take place. So we've got 5 things here that all change how fast reactions can happen. If you change the temperature of a reaction, that's going to change how fast the reaction is able to take place. Increasing the temperature increases the reaction rate because you have more collisions. Same with if you decrease the volume or increase the pressure, basically squeezing all those gas molecules closer together, you're going to increase the reaction rate that way. Increasing concentration. So if you have a gas that has a concentration of 1 mole per liter, if we put in 2 moles per liter, you're going to have a faster reaction rate. The reason why all of these things increase reaction rate is because you have more collisions. And some of those collisions, like if we increase the temperature, that's going to also give the collisions more energy. But all of these things increase the number of collisions. And the more collisions you have, the faster the reaction is able to take place. Increasing the surface area, we're talking about basically just if you smash things up into smaller pieces, they're going to react faster. So sugar cubes, let's draw a picture here. Sugar cubes versus sugar all smashed up into tiny pieces. Here, you're only able to react with the sugar molecules that are on the outside of that sugar cube. But when you smash it all up into pieces, then you're able to react. All of those things are able to have collisions with other molecules and react. So smashing things up into smaller pieces also increases the reaction rate. Now, catalysts we'll talk a lot about in a different section. I know you guys know about catalysts. They speed up the reaction because they lower the activation energy. So we're going to talk about that. When we look at reaction rates and describing how fast reactions take place, we're going to talk about that in terms of molarity per second. Remember, capital M is molarity, and actually specifically we should talk about delta. So that triangle, anytime you see a triangle in any equation, it represents change. So how does that molarity change over time? And as that molarity changes, that's going to tell us how fast the reaction is taking place. So we're going to be talking about how the molarity decreases over on our reactant side and how the molarity increases as products are produced over on the product side. Okay, so let's take a look at concentration here. It says, in this example, we've got 2 nitrogen dioxide molecules over on my reactant side. Decomposing, this is a decomposition reaction, producing nitrogen monoxide and oxygen gas. That does look balanced. I've got 2 nitrogens on each side, 4 oxygens on both sides. So what happens to the concentration of the reactants and products as the reaction progresses? So the reactants are going to decrease in concentration. The products are going to increase in concentration as the reaction progresses, and it's going to keep going. And the reactants will continue to decrease until eventually it reaches 0, and the products will increase at that exact same rate as well. So in our previous unit, Unit 4, we talked about how these coefficients here, we used them as mole ratios. So when we talk about reaction rates now, we're going to use those coefficients to help us compare the rate at which things appear or disappear. So let's take a look at this. If the rate of oxygen production is 3 times or 3.2 times 10 to the negative third molarity per second. What is the rate of disappearance of NO2? So here's what that problem is going to look like. It's going to look just like a mole ratio problem, except for we're dealing with molarity per second units instead of moles or grams or whatever it is. So we're going to start with what we're given, 3.2 times 10 to the negative third. That's the molarity per second rate of production of oxygen. And so we're going to set up our units to look just like that. And then since my coefficient in front of oxygen is 1, instead of using mole ratios, we're using rate ratios. So for every 1 molarity per second change of oxygen, there's going to be, we're talking about NO2 is what we're looking for. So 2 molarity per second is going to be the rate of change of NO2. So all we're doing here is multiplying across, multiplying by 2, so we get 6.4 times 10 to the negative third molarity per second. One thing to make sure that you pay attention to when you're doing this problem is to recognize that this is the rate of disappearance of NO2. Disappearance because NO2 is our reactant up here. So reactants disappear and products are produced. And so we talk about the rate of appearance or the rate of production for our products. We talk about rate of disappearance, which is basically how fast it's getting used up. You're getting a molarity changing of 6.4 times 10 to the negative third moles per liter per second change of nitrogen dioxide. All right, there are two different types of rate laws, and so we're going to talk about one in the video notes today, and then we're going to talk about one in class next time. So we're going to talk about the differential rate law today, and all of these, there's the differential rate law and the integrated rate law. These all come from calculus-derived equations. That's not something that you have to worry about, but you do have to know how to use them, and then what the different parts of the equation represent. So we're going to be talking about the differential rate law today, which is the basic rate law. Whenever you see equations and it asks you, or questions and it asks you to find the rate law, this is the one that it's talking about. Rate laws are just equations, and differential rate law shows how the rate of reaction depends on concentration. The integrated rate law shows how concentrations depend on time. So we're going to look at, you can write this up above in your notes depending on what you have room for, the general formula for the rate law. So rate laws are just equations. Our differential rate law equation looks like this. This is the general formula. Rate is equal to K times, and if I have an equation that looks like this, A plus B, and then I have products C and D. Products are not included in rate law equations at all. So my rate law equation looks like this. Rate equals K times, and I'll explain every part of this, the concentration of A to some power that we have to figure out, times the concentration of B to some other power that we have to figure out. Now, let's see. Rate is going to be in molarity per second. K is going to be what is called the rate constant. And we're going to talk about those units here in just a minute, because the rate constant can have different units depending on what the reaction is. Anytime you see brackets, that equals molarity. And so this is going to represent the concentration of A and the concentration of B in molarity. When we look at different chemical reactions, they're what are called orders of reaction, depending on how these concentrations here, how those concentrations affect the rate of the reaction, determine what are called the order of the reaction, the order of the rate law. So there are what are called zero order reactions, first order reactions, and second order reactions. So zero order reactions have a constant rate, meaning the concentration doesn't matter at all when we talk about our rate of change of the reactant. The equation is going to look like this. When we have zero order reactions, we're going to have rate is equal to K times A to the 0 power and B to the 0 power. So notice zero order reactions have exponents of 0. Now anything to the 0 power is just 1. So then my equation is just going to turn into rate equals K for zero order reactions. First order reactions, we're going to have the reaction rate is proportional to the concentration of just one of the reactants. So you're going to have equations that look like this. Rate equals K times the concentration of A to the first power, which we don't have to write the first power. We can just leave that off, and it basically means the same thing. Or if we have two reactants, rate is equal to K times the concentration of B. So only one of the reactants in this case is going to affect the rate of the reaction. The other one doesn't. Second order reaction, we've got a couple of different options here. The rate is proportional to the square of the concentration of one of the reactants or the concentration of both. So we have options that look like this. Rate equals K times A to the first power, B to the first power. So if you notice, when we add those exponents together, they equal 2. Or we can have rate is equal to K times A squared, or rate is equal to K times B squared. So there's this square relationship between the concentrations and the rate of the reaction, how fast the reactants are getting used up, how fast the products are being formed. So we're going to have all of these different forms of equations. Basically, in rate law problems, our job is going to be to figure out what do these exponents equal, and once we figure out what they equal, then we can figure out the rate of the reaction and figure out all kinds of other things. If we're looking at graphs for zero order, first order, second order reactions, specifically with, now these are graphs, you have to pay attention to what's on your X and Y axis here. So notice on my Y axis, these are my rates. This is how the molarity is changing over time. And on my x-axis is all concentration. So notice for zero order, as the concentration increases, the rate doesn't change. For first order, as the concentration increases, the rate increases as well, in a linear relationship. For second order reactions, as you increase the reactant concentration, the rate increases in a square relationship. So those are the graphs when we graph rate versus concentration. Okay, next thing, and really important, is to talk about the units of K, our rate constant. They do depend on the order of the rate law. They are not always the same, and really important on the AP exam, they always like to ask you, to solve for the rate constant and to specify what the units are. The units are always a point all on their own. So they are things that you either need to memorize, or if you can figure out how to solve for what those units are, then it becomes easy really to understand. So let's take a look at, let's do a second order reaction just to see how to figure out these units. So remember that my second order rate law looks like this. Rate equals K times the concentration of A times the concentration of B. So here's how we can do a little unit analysis to figure out what the units for K are. For rate, we're just going to plug in units for everything. So let's remember that rate is molarity per second. And my units for K, I'm just going to put parentheses here. And we're going to do all of our units in fractions. And I'm going to figure this out in just a minute. Remember, anytime we see brackets in our rate law equation, this represents concentration. So I'm going to have molarity are my units for the concentration of A. And I'm just going to say anytime you have units that don't have fractions in them, we're going to put them over 1. So molarity over 1. For B, those have units of molarity as well. So I need all of my units over here on the right side to multiply together to equal my units on the left side. So basically, I've got seconds over here on the bottom. So that means I need seconds on the bottom somewhere. So I'm going to put those right there. Also, I've got 2 molarity. That's molarity squared on the top. I need one of those molarities to cancel to only give me 1 over here. So I'm going to put a molarity down there, and that'll cancel out one of my molarities, and it'll leave me with molarity over seconds, which are what my units are for rate. So Now my units for K are 1 over, I'm going to put ms first. Now, these are my K units. Remember, the AP exam doesn't like to put units in fraction form, so they'll write it this way instead. Molarity minus 1, seconds minus 1. So these are my units for second order, units for the rate constant for K. First order, you have molarity over seconds equals this times molarity over 1. So then basically I just need seconds on the bottom will give me molarity over seconds. So my units for K, first order, are 1 over seconds, or S minus 1. Those are my first order units. Zero order reactions, K units, are just molarity over seconds. Okay, so we're going to go ahead and take a look at a rate law problem. This has the series of steps that you need to follow, but just having the series of steps written out in your notes doesn't really help you. So I'm going to go through one of the examples. So, and we're going to go through each step. So reading through the steps actually doesn't really help. So let me just skip over to the example and then we'll see what this looks like. Okay, so here's what rate law problems look like. You are given all kinds of information. You're given an overall reaction here, and I'm given a bunch of data. So the only reason the only way you can figure out rate law equations is by analyzing some data that's given to you. So notice that the question says, write the rate law given the following data. Now, the rate law is just an equation, and remember the general format is going to be rate equals, that's an equal sign, K, and then the concentration. Now in the general formula, I was writing A's and B's and all that stuff, but now I actually have formulas of reactants. So it's going to be K times the concentration of my first reactant, which is NH4 plus, to some power of X, times the concentration of NO2 minus to the exponent of Y. And our job is going to be to figure out what is X, what is Y, and then we can figure out the order of the reaction based on those exponents, if it's zero order, first order, or second order. So here's what we're going to do. We're going to take a look at a couple of these experiments here. And I'm going to pick two experiments where the concentrations are the same for one of them, but not the same for the other. So I'm going to take experiment 2, and I'm going to plug in all of these numbers for experiment 2, and I'm going to put it over experiment 1, and we're going to cancel some stuff and solve for one of the exponents. Here's what that looks like. So I'm going to take experiment 2 first, and here's my rate information. So experiment 2, my rate is 2.7. times 10 to the negative 7. That's my rate, and that's equal to K times, and my concentration of NH4 plus, that should be a plus right there, is 0.1 to the X, and then for NO2 minus, it's 0.01 to the Y. Now I'm going to do the exact same thing with everything from experiment number 1. So experiment number 1 has 1.35 times 10 to the negative 7 equals K times, and then my concentration for NH4 plus is 0.1 to the X, and then I have 0.005 to the Y. So now I'm going to look for things that cancel. So I've got K cancels out, and my NH4 plus stuff cancels out, and I end up with, and I'm going to divide this, so 2.7 times 10 to the negative 7 divided by 1.35 times 10 to the negative 7, that's 2, and then equals 0.01 divided by 0.005 is 2 to the Y power. So then Y is equal to 1. So that means my exponent here is going to be 1. Okay, then I'm going to go ahead and I'm going to do, now I know y is equal to 1. Now I need to do the same thing to figure out x. I can pick any two experiments this time because since I already know y, it doesn't matter which two experiments I use. I can use one where the y's cancel, but if they don't cancel, no big deal because I can just plug in y for that number. So I'm going to go ahead and I'm going to pick 3 and 1. And I'm going to go ahead and plug in the same information just like I did up above. So for experiment 3, it doesn't matter if you do 3 over 1 or 1 over 3. I just usually like to pick the one with the bigger number and put it on the top, so then I'm dealing with whole numbers instead of decimals. But it'll still work out mathematically the same way. So my initial rate for experiment 3 is 5.4 times 10 to the negative 7. Equals k, then I have 0.2 to the x, and then 0.01 to the y. That's all of experiment 3 stuff plugged in. Experiment 2 stuff, I'm going to have 2.7 times 10 to the negative 7 equals k, and then 0.1 to the x, and then 0.01 to the y. So this time I have different things that cancel out. I have my y stuff that cancels and my k stuff that cancels. So here again, 5.4 divided by 2.7, that's 2. And then I get equals 2 to the x. So x is also equal to 1. So we're doing all of this work just to figure out, basically, if we get exponents of 0, you're only going to get 0, 1s, or 2s for your exponents. So that's what we're looking for. This equation is asking me to write the rate law. So when I do that, all I have to do is take my exponents and plug them back into this equation here. So then my rate law equation is rate equals k times NH4 plus to the first power, but we don't have to write 1s, right? So we know that that's there automatically if I put NH4 in. Then NO2 minus. So this whole thing is really the answer to this question, right? The rate law for the data that's given. It gives me first order with respect to NO2, first order with respect to NH4. Overall, this reaction is a second order reaction. And once you know what the equation is for your rate law, so I have that rate is equal to k times NH4 plus times NO2 minus. Once you know your rate law equation because you know your exponents, then it's going to ask you to do things like to solve for k. What is the value of the rate constant? From there, all you have to do, since you know what these exponents are, you can just take any experiment and you can plug in that data to this equation and solve for what that k value is. So I'm going to go ahead, it doesn't really matter what experiment you pick. I'm going to go ahead and pick experiment number 1, and I'm going to plug in all the data. So the rate for experiment number 1 was 1.35 times 10 to the negative 7, and I don't know k, that's what I'm looking for to solve. The concentration of NH4 plus was 0.1 to the first power. The concentration of NO2 minus is 0.005, also to the first power. So then we can go ahead and solve for k. Solving for k here is going to give me an answer of 2.7 times 10 to the negative 4. Now, k units. Remember about k units that they depend on the reaction order. This is a second order reaction. We already talked about how to solve for k units. So looking back in your notes earlier, when we had a second order reaction, those units are 1 over molarity seconds, or molarity minus 1 seconds minus 1. So this is our final answer here. All right, we're going to do a lot of practice of these in class, so go ahead and make sure that you bring your notes with you to class next time, and we'll practice some of these rate law problems. So I will see you guys in class.